Today, lesson 25B, day number 2 of the scientific notation. Yesterday, our focus was on operations where we were multiplying and dividing things that were written in scientific notation. Today, our focus is on adding and subtracting things that are in scientific notation. So, background knowledge, remember a number is in scientific notation if we have, and we typically call that normalized scientific notation. If we have a number between 1 and 10 times some power of 10, and scientific notation is a way for us to write very large numbers and very small numbers in a compact form. So today our focus is on adding and subtracting. And the idea of adding and subtracting really revolves around the idea of combining like terms. Like if you look up here, I have 5x cubed plus 7x cubed. We all know that that is 12x cubed because we are combining x cubes. We are combining like terms. And that comes from the fact that we are adding 5 of the x cubes and 7 of the x cubes together. Well, if we have two numbers that are in scientific notation that we're trying to add together, that's exactly what we are doing here as well. We have 5 of the 10 to the thirds, and we are adding on to that 7 of the 10 to the thirds. And what I'm doing right now is I'm breaking it down, trying to show you that it really is exactly the same thing. We are trying to combine like terms. So that's how we end up with 12 times 10 to the third for this problem. Now, if you were asked from there to write your answer in scientific notation, you would have to do a little bit of adjusting like we did yesterday. But I'm not going to worry about that, I don't think, in this problem. We're going to find out in a second. I guess not. So adding and subtracting work exactly the same way. It's more about combining like terms. So if I had 17w to the ninth minus 9w to the ninth, that's 8w to the ninth, because we are combining like terms. Well, if I had 17 times 10 to the ninth minus 9 times 10 to the ninth, same idea. It's all about combining like terms. And when you combine like terms, you have to make sure that the base is the same and the exponents are the same. That's how combining like terms works. Okay? So if the bases are the same and the exponents are the same, you may follow the rules of subtracting, or in the previous problem, adding expressions or combining like terms. And then we have a generic form of this, looks kind of like this. But if you went back through those previous two problems, that's essentially what I had there. All right. Remember, the bases must be the same, and the exponents must be the same. Everybody go ahead and try 1 through 4. All right. Number 1, obviously, is 8.2 times 10 to the third. Number 2, and remember, we need to check to make sure that the things that we are combining together have the same base and the same exponent, because then, essentially, we are dealing with like terms. So number 2 is 2.2 times 10 to the negative 2. Number 3 is 1.97 times 10 to the 14th. Number 4, we end up with 14.1 times 10 to the negative 5, but the instructions do tell us to make sure that our answer is in scientific notation. And so we need to make a bit of an adjustment like we did yesterday. So we need to make sure that we turn 14.1 times 10 to the negative 5 into 1.41 times 10 to the negative 4. We made the 14.1 smaller by 1 power of 10. Therefore, we've got to make the 10 to the negative 5 bigger by 1 power of 10. So that's pretty easy. Take a look at number 5. Now, notice in number 5 that we have a slight issue here. What's different about number 5 compared to 1 through 4?
The exponents aren't the same.
Yeah, the exponents aren't the same. So what that means right now is we don't have like terms. That would be like trying to combine x cubed with x to the fourths, and we can't do that. So what we're going to have to do here is we're going to have to make a slight adjustment here. So what we can do is we have two different things we could do. And what we have to make sure we do is we have to make sure we create like terms. So in other words, we either need to turn the 7.1 times 10 to the fourth into 10 to the thirds, or we have to turn 3.4 times 10 to the third into 10 to the fourths. We have to make a slight adjustment here. I'm going to do this both ways. So notice that on the left-hand side, I turned this into this. Now, how did I do that? Well, much like taking something that's not in scientific notation and turning it into scientific notation. So if I wanted to turn 10 to the third and 10 to the fourth, I made that bigger by 1 power of 10. So I've got to make this one smaller by a power of 10 to sort of counterbalance that. So now I have like terms. Notice that I have 10 to the fourths and 10 to the fourths. So now I can utilize this idea of combining like terms. Now I also instead could try and create terms that were in terms of 10 to the third power. So that would mean I would have to make an adjustment to the 7.1 times 10 to the fourth. So if I'm going to do that, and I want to turn that into 10 to the thirds, that's making it smaller by a power of 10. I would have to make that bigger by a power of 10, and that would give us this. So now let me finish the left-hand side. That would be 7.44 times 10 to the fourth. On the right-hand side, that would give me 74.4 times 10 to the third, but then if I turn that into scientific notation, you can see that I essentially end up with exactly the same thing there. You have a choice. Either make an adjustment on the first expression or the second expression, but the idea here is that you must create like terms. Any questions about what I did on number 5? All right, let's try this one problem at a time here. Everybody go ahead and try number 6. So in this one you have a choice. You either need to turn them both into 10 to the negative 1 power or both into 10 to the negative 2 power. And having said that, it doesn't matter. You could turn them both into 10 to the 4th power if you wanted to. You just have to make sure that you create like terms. I'm going to turn it once with both of them as 10 to the negative 2 power. So that meant that I had to change this. So since I made this one smaller by a power of 10, I have to make that one bigger by a power of 10. That's why 2.5 turned into 25. Now I have like terms there. And I also could turn them both into 10 to the negative 1 power. So if I'm going to do it that way, I changed this. I made it bigger by a power of 10. Therefore, now I need to make that smaller by 1 power of 10. Either way, doesn't matter. Just make sure that your answer is in scientific notation. The one on the left, I didn't have it in scientific notation. I'll have to make one more change. The one on the right happened to automatically be in scientific notation when I combine like terms. Either way, doesn't matter. But you should have ended up with 2.62 times 10 to the negative 1 power. Any questions about number 6? All right, go ahead and try 7, 8, 9, and 10. And then we will compare those with our shoulder partner. So for number 7, we should end up with 2.73 times 10 to the negative 5. Right now, they are not like terms. We have to create like terms. So one thing I could do is turn this into a power of negative 5. I made that bigger by a power of 10. Therefore, I've got to make this smaller by a power of 10, much like we did yesterday. So now I have like terms. 2.2 plus 0.53 is 2.73. All right, number 8. Morgan, what did you get?
For number 8, I got 7.25 times 10 to the 5th.
Very good. Any questions on number 8? John?
I did it so I changed 4.5 times 10 to the 4th to 10 to the 5th.
Okay, so you made this 10 to the 5th. You made that bigger by a power of 10. Therefore, you've got to make this smaller by a power of 10. Right? So that's 7.65 times 10 to the 5th. Lauren, number 9.
I got 8.21 times 10 to the negative 3rd.
All right. Any questions with that one? Sam?
1.39 times 10 to the negative first.
That does not sound right to me. Alicia?
Number 10, right?
What's that?
We're on number 10.
We are on number 10.
Okay. 5.6986 times 10 to the second.
Good. All right. Any questions about why number 10 is that? Yes.
I just got 5.686, not 6986.
Well, let's see here. So I had to turn this. I can see by the answer that we need to turn it into 10 to the second. So I made this bigger by a factor of 10 to the third power, right? So that means I need to make this smaller by a factor of 10 to the third. So that means I need to basically move the decimal. I'm going to use this space up here 1, 2, 3 times. So that is 0.0014. So now I have like terms. And we are subtracting. So I'm pretty sure that that is correct. All right? Any questions about any of these four?
For number 9,
Yes.
what if you change both of them to negative 1?
Okay, so that would make, I made this bigger by a factor of 10, right? So I have to make this smaller by a factor of 10. Now we have like terms. 8.4 minus 0.19 is 8.21. Okay? We good? Yes.
If we were to turn them both into the negative 2 exponent on number 9,
Okay.
the answer would be different.
Well, the answer that you get would be not in scientific notation. See, if you turn this into 10 to the negative 2, which is a fine starting place, you made it smaller by a power of 10, so you've now got to make this bigger. So now you have 84 times 10 to the negative 2. So if you subtract 84 minus 1.9, that is 82.1. So we have 82.1 times 10 to the negative 2, but that's not in scientific notation. When you turn it into scientific notation, you end up with this. All right, we good? It doesn't matter which power you turn them into, but you need to make sure that your answer is in scientific notation. All right, next thing. What if numbers are in different forms? In other words, what if we had something like this, 3.5 times 10 to the negative 2 times 0.0012, and you were asked to write your answer in scientific notation? What should you do?
Change the second one into scientific notation.
Yeah, if you turn this into scientific notation and then do what we just did in the previous 5 problems. Everybody try number 11. Okay, so we turn 0.0012 into scientific notation. This is a multiplication problem. So at this point, we can put our 3.5 and our 1.2 together and multiply using the commutative property. And then 10 to the second times 10 to the negative 3, we add exponents when we're multiplying. I suddenly have shifted from adding and subtracting to multiplying, but it shouldn't matter. We've got to remember what we talked about yesterday. Okay? 4.2 times 10 to the negative 5, yes?
So you don't have to change the exponents and multiply.
No, because multiplying, we don't have to have like terms, only when we're adding or subtracting. Okay? All right, everybody try number 12. All right, so 5,100 is 5.1 times 10 to the third, and once again, now we have a problem like we talked about yesterday. You would want to group these two together to divide, and then we subtract exponents when the base is the same, and we are dividing, and so that would be 3 times 10 to the first. All right, go ahead now and try number 13 and number 14. Do both of them, please. Now notice in 13 and 14, 13 is adding, 14 is subtracting. All right, so remember when we're adding or subtracting, we have to have like terms. So I'm going to turn 570,300 into a power of 4. So most of you probably started with turning it into scientific notation, but I knew we needed it to be a power of 4 as far as the 10 to the power of 4. From there, I don't know why that says multiplication. It should say addition right there. And then from there, we deal with our 4.72 plus 57.03, which is 61.75 times 10 to the fourth. Now I need to turn that into scientific notation. How about, Brandon, number 14?
I got 3.4 times 10 to the fourth.
3.4 times 10 to the fourth. Let's see if that is correct. I turned 51,000 into a power of 4, and I went ahead and turned the 170 times 10 to the second into a power of 4. And the reason why I did that was because putting this in scientific notation is 5.1 times 10 to the fourth. Now I have like terms, and that would be 3.4 times 10 to the fourth. Any questions about either one of those two? So I guess the biggest issue here is making sure you're paying attention to whether you're adding, subtracting, multiplying, or dividing. All right, last thing for today. And I don't know whether you've talked about this in science or not, because I know you guys deal with very, very large numbers sometimes in science. But one of the standards is, what do you do when you multiply huge numbers on a calculator and take what your calculator shows and somehow determining what that really means? So could I have all of you take 5 billion times 5 billion on your calculator? And I'm sure at some point over the last few years, it may have been by accident, but you've maybe typed some numbers in and you had something that looked like this. I'm sure at least a few of you have seen something like this. Well, this is your calculator's way of giving you scientific notation. Okay? So when you type that in, your calculator showed something like this, correct?
No.
Yes?
Mine says 2.5
Well-
times 10 to the 19.
Okay, you have a better calculator than mine. Yours already shows it that way. But if you're using my calculator, this is what it looks like. Well, what that means is that is my calculator's way of scientific notation. Okay? So what that means in scientific notation is 2.5 times 10 to the 19th power. Okay? So let's do a little bit of practice with that. Everybody go ahead and type in 15, 16, and 17, and then write down what it really represents in scientific notation. Like this, 3.47648 times 10 to the 14th. We made a determination that we'd like to maybe start rounding these to the hundredths place. So if we're going to do that, that would be 3.48, because this is the hundredths place and that digit is 5 or bigger. So 3.48 times 10 to the 14th if we're going to round to the nearest hundredth. Number 16 should be 3.15 times 10 to the negative 12th. 17 should be 7.15 if you round to the hundredths place times 10 to the 18th power. All right, we are finished for today.